a better information coordination. So that would obviously lead to lesser amount of surgical errors. So that is why we finally focused. And we did read about ergonomics in terms of um, practice, academic practice. So we thought we will work much on the ergonomics perspective of the human hand. And from there, we will try to expand into our research and we'll see how the lines meet over there. So understanding this, we took hand anthropometric data of about 120 people. And then because we wanted to bring down a sort of standardization when we are trying to develop a surgical tool for laparoscopic opinal surgery. So that is where we started exploring. And this is the existing laparoscopic tool. And as I mentioned to you at the very beginning, we don't work anything under the skin. So that is why we decided we are not going to work or do any changes on the surgical tool which goes under the skin. And we decided to work only on the outside portion of the surgical tool. So this is where we started with the work. So understanding that, we tried to explore the existing laparoscopic tool, and we did happen to have at least some 50, more than 50 iterations in terms of designing it. So once we are fine with a particular design, we tend to take it to the gastroenterologist or the surgical people um, who use the laparoscopic tools for surgery, and we tend to get the feedback from them. If for any fine tuning is required, then we tend to reiterate the design. So like this, we happen to come across around 50 plus designs, and this was the 54th design that we finally narrowed down to. So this was the final concluding design. So if you look at it, you have the positions for three fingers, which goes in here. The fourth finger goes here, and this is for thumb because a thumb is very much essential for indexing, and that is the region where it tends to point out in a very accurate manner. So we use thumb as a separate region. On top of it, when we discuss with the surgeons, they tend to say that ergonomically they felt the existing design of laparoscopic surgical tool had some difficulties. Like sometimes the surgery goes for, on average, it goes from for 4 hours, but sometimes it also tends to go for about 8 hours. So you can imagine that if you're holding a scissor like equipment for continuous 8 hours, you can imagine how tedious it would be. So most of the surgeons that we spoke, they tend to say that after the surgery is done, they tend to take some sort of painkiller so that they can overcome the pain of the wrist, because the current surgical tools, they had some issues in terms of holding it, and they need to hold it with yeah, a fixation on wrist. So we wanted to overcome all those issues. So that is why we worked on developing this particular design, and we believe so after continuous iterations and interactions, we came down to this particular surgical tool, and then we 3D printed it. So this was the one which we 3D printed using an FDM technique, wherein you can see the actual material and the support material it got printed. So this was with the actual and support material. This is why we have cleaned the support material, and this is the actual material or the final part. And this is the part that we fixed on the existing laparoscope tool. So all we did is we removed the traditional laparoscopic handle and we replaced with the current handle that we have devised. And the idea behind this is at any point of time, the surgeon feels he or she is not comfortable with the existing tool. They always have the freedom to remove this portion of the tool and they can go for the market available one, and they can just replace it with the one that they have removed. If they're fine, they can keep going on performing the operation. So that's how we design. So here you can see this is how the um, tool looks like when it goes for application. So you can put in 4 fingers plus the index finger goes in separate, and we have given a separate grip. And with all these activity, we have improved the surface area of contact as well. So that means that now, as compared to the previous 2-point contact, now we are having a more or a better amount of information that goes through the palm or through the surgical tool, and now they are in a better position to get a feedback in terms during the operation time. So this is the difference between the existing and the modified one. And then nothing have changed except for the input. As I have mentioned at the very beginning, there are different types of hands. So then we thought, what is that we are doing for the type of hand? So then we came out with an option of putting the inserts. The inserts are nothing but the rubber-based profiles. We tend to have this as a standard surgical tool that we have devised. On top of this standard surgical device, we tend to put the inserts. The inserts goes in here and here. What insert do is, like, based on different hand profile, we tend to scan the hand profile. We tend to take the data of the hand. Like, let us say we have female hand. So both of them, for each of them, we tend to develop a separate insert. So this is for a thin female hand, and this is for a thick male hand that we have taken as a case example. So you have two different inserts based on the type of profile of a hand. Like, let us say this male, when he goes for an operation, all he need to do is this insert is given to him, understanding his hand profile. But from the data obtained from the hand profile, this insert is printed. So when he goes for the operation, all he need to do is he need to put these inserts over here. He can remove off this because these inserts are completely customized for that particular person. When the next person, let's say the female um, comes in, she can put his insert over here and she can perform the operation. So now that the entire surgical tool is transformed to improve surface contact, and further to it, it also have been designed to the exact hand profile of the person or the surgeon who tends to perform the operation. So that's how it has been designed. So this is this we printed it through the polyjet technology. As I mentioned, you can change the show hardness. So this is why we tend to change the show hardness based on the particular person's hand profile and the person's requirement. The rubberiness or the show hardness has been changed and these inserts have been developed. So being from the mechanical perspective, we wanted to make sure the tool doesn't break at any point of time for the given loads. So we did happen to perform an answers analysis and the tool was put in for application. So this, after putting the tool for application, we tested the tool against a couple of parameters, namely towards grip, functionality, comfort, wrist posture. So we compared it with the existing, with the modified one. So this was the data that we obtained for the existing one, and this was the data that we obtained for the modified one. And it seems like the modified one performs, or we tend to can be seen from this chart, that the modified one felt more comfortable as compared to the existing one. And this we, from the academic perspective, this particular research work was also published in one of the leading rapid prototyping journals or the additive manufacturing journals. If you are interested to explore more, you have these papers. From there, you can take it up. And the next case study that I'd like to take you through is on the diabetic foot. So we all know diabetes is the fourth leading cause of death, and by 2030, 439 million people were projected to get affected by diabetes, and India ranks high in terms of diabetic. And we know diabetes is one of the major issues that is going on now. And we as well know somebody who is very close to us or someone in our family is also diabetic. So that's how diabetic is spreading out globally and with in and around us. So understanding this, we thought we'll do a sort of research to explore what we can do in terms of diabetes. So that is why we started with this. And for this particular research, we went through questionnaire and we tend to participate in diabetic foot camps or diabetic camps wherever it is conducted. For this particular research, also we worked with two different hospitals around Coimbatore, and that was the source of data for our research. And we used about 2,570 respondents, of which you can see the spread of male and female population. And we tend to observe what were the complications that diabetic people tend to face. And some of the common complications that we came across was high blood pressure, foot problems, and then we tend to find the combination of issues. Like people with blood pressure, they also had foot problems. People with neuropathy had foot problems. People with heart disease had foot problems. So foot problem was found to be one of the major issue for people who tend to be diabetic. And even if you observe with your close ones, they would always say that the morning, by they tend to have a tickling feeling in the limb, or a sort of itching sensation in the plantar surface of the foot. Some sort of they tend not to have sense in the bottom portion of the plantar surface of the foot. So this was very quite common thing for diabetic people. So that is why we did happen to understand, yes, in market there are some custom insoles that are available. So for that also we conducted how many of them are aware of custom insoles, and roughly about 54% of the population that we inquired or surveyed, they weren't aware of the custom insoles. So then we realized, yes, diabetes is something very much crucial, and obviously we need to do something in terms of customization perspective, so that we can treat the diabetic patients. So saying that, our idea is not to overcome diabetes, but in order to buy time for the people who are diabetic before getting into the food problems. That was the primary idea of our focus. So what happens with that, with a diabetic foot? So ideally, a person who has diabetic, they ideally start with diabetic neuropathy. So in their foot, as the foot tends to touch on the surface, the thing, the skin underneath their foot tends to get thickened, and the skin which is thick, it tends to close the nerves which are taking in the blood. I mean, which are taking the blood from the heart to the bottom of the foot. As it gets closed, and that is where the entire issue starts. So as the blood flows, so this is for a normal foot and this is for a diabetic patient. As the person is normal, his tissues are fine, his skin is fine. But once he becomes diabetic, and because of the property of the entire property of the skin changes, and for which the skin doesn't it tends to become so soft afterwards, and it doesn't take the load when the person walks. So as he puts his foot down, it tends to close the nerves, and as it closes, it tends to damage the nerve, or it completely stops the flow of blood as the nerves gets closed. As the flow of blood gets stopped, ideally, what should happen is the blood which is coming to the bottom of the foot, it should need to go back to the top. Whereas once the nerves tend to get closened, it doesn't happen. So whatever the amount of blood that came down, it stays there. It gets stagnated. So we all know that the stagnant water is the one which causes most of our pus. So in the same manner, the stagnant blood which stays at the bottom of the foot, it starts with gangrene, and once the gangrene spreads, it becomes untreatable. So that is why they tend to go for complete amputation of that particular portion of the limb, which were not which could not be treated. So this is what tends to happen, and this is the stage just before going for amputation, wherein you can find a person foot. Sorry, the person foot is cleaned over here because of the pressure ulcers. It tends to cause foot sores, and you can see pressure wounds, pressure ulcer based wounds. So coming back to the topic, like what does a mechanical engineer has to do with this? We all know that if you take a pointed surface and if you put load on top, and if you try to move that pointed surface, the wear rate is very high because the surface area of contact is very low over here. So obviously the surface wear would be very high. Whereas the moment we tend to improve the surface area of contact, what happens is the load distribution becomes a bit better as compared to the previous case, situation one. Now, if we take a person who is weighing about 90 kilos, so theoretically 45 kilos need to go to the left and 45 kilos need to go to the right foot. So that is the idea behind it. So both the limbs tend to take, or both the plantar surface of the foot need to take the weight of 45 each. But in reality, if you look at the surface area of foot, it is not of a flat or it is not something very clear wherein you can take the entire load of 45 kilos. It can, we can see from the surface area of foot because that some portions are projected and some portions are curved in. So for that reason, if we further narrow down, we can understand that only 40% of the foot tends to take the load, whereas the rest 60% of the foot surface doesn't come in contact with the ground. So thereby it doesn't take the load. And that is one primary reason wherein we can explore that. If we turn our shoes, it tends to get worn out at only certain regions, while other regions are not worn out. The current practice is when we tend to go for purchase of shoes, our foot is measured only in terms of length, and very rarely it is measured in terms of width. So that is the only measurement that has been taken over the foot. But theoretically, there are three types of foot that we all are being categorized as. One is the flat foot, second is the normal arch, and third is high arch. What flat foot is? Like people who are generally bulky are the ones who tend to have the flat foot, or a very lower amount of people, maybe around 5% of the children are born with flat foot. And the second case is the normal arch. Most of them tend to be or tend to fall under the category of normal arch, wherein they tend to have a sort of arch in their foot. Whereas people with flat foot, they don't have an arch like the other two types. A foot tends to be flat, and this is what the imprint would look like when a flat foot person walks. So this is for a normal arch wherein you tend to have a slight arch, and this is otherwise the high arch, or it is also called as the athletic foot, wherein people who are very thin and who tend to you know be athletes, they tend to have this high arch. So these are the three major categories. And when we tend to go for purchase of shoes, we don't measure what is the foot type, but we only bother for what is the length of the foot, and we our purchase is based on the length of the foot rather the type of the foot. So here there are two things. One is the surface area of contact is better. Automatically, the load distribution will be better. That is what we saw from the pointed one to the improved conical shape. And second one thing is our foot is not of a regular profile. So we need to understand the profile also plays a role in terms of wear. So wherever the highest or the pointed area on the foot is, that is where the highest amount of wear and tear is. So therefore, that is the region where the friction is more, and so therefore we need to do something in terms of overcoming that. If you look at us in terms of load perspective, we straight away we undergo two major types of loading. One is the static load, and the other one is dynamic load. We stand, we tend to go on the static load, and when we move, run, walk around, that we fall under the category of dynamic load. So the load distribution also plays a major role when we tend to understand about the foot. Yes, as I mentioned earlier, the market available custom insoles are there, but they are not really custom insoles. They are insoles which have been already um, placed according to the size, but it doesn't understand or it doesn't have a clear indication based on the type in which our foot insole or our foot plantar surface is. Because only when we do an insole according to the plantar surface of a foot and based on the activity that we undergo, then only we can say it as a custom insole. Other than that, it is again a sort of mass customization. So this is more of a mass customized product rather a completely customized product. And if you look at the population, here there is a very wide range. Let us take these two people. If you consider their foot size as 7, ideally these two people's foot size might be 7, but the amount of activity, the type of loading that they undergo is completely different, which is not studied when it comes to mm, developing the custom insole. So our focus is to study the different types of loading, how we can improve the surface area of contact, how we can reduce the wear rate. So these were some of the parameters which we considered for that. And of the entire population, if we just take one person, his shoe size changes from time to time. Maybe once he reaches an age of around 24, 25, he tends to attain a foot size, and that would stay the same throughout his lifetime. But let us say if the foot size becomes 8, and the 8 foot size will remain until the last day. But whereas the amount of activity that he or she would undergo is completely different from time to time. And again, from time to time, once in every 6 months, our body profile changes, our weight changes. So we need to do some sort of complete customization to our shoes or the footwear. Else, it is of no point in performing the right aspect of the focus in terms of treating the club, um, diabetic foot. Many people can say like in my grandfather days or great grandfather days, there was no big fuss about customizing the foot insoles, and they walked on the fields. They were farmers and they never had any issues. So we also had this question, and we tried to understand what was happening during that time. So if you look at the period in which they were around, it was like either they walked barefoot on grass, barefoot on mud or clay, and barefoot on sand. So what was happening over here in all these situations, the ground underneath, it tends to change the profile according to the type of the foot. The ground tend to change the profile according to the type of foot. So that way the entire load is being taken by the ground. So that was happening on the other side. Whereas in current scenario, we walk on flat surface. So, so the load doesn't get shared. Not only from this perspective,
50%
um,
90% details, 50%.
would Divya be able to switch off the mic, please? We also tend to do our analysis from the gauge cycle perspective, wherein gauge cycle is nothing but after an age of 5, we tend to get our own gauge pattern, wherein we tend to walk to leaning towards the left or right. That is ideally called as the gauge pattern. And we also took into consideration the gauge cycle when we tend to perform this research. And we also studied what is the amount of time that our foot lays on air and what is the time that it tends to hit the ground. So undergoing that, we realized that 60% of the time when we are in a dynamic mode, our foot is in the air, and only 40% of the time our foot is in contact with the surface. So understanding all these parameters, we started with this research. So in order to do this research, what we did is we asked a person to walk on an EMED platform, wherein EMED platform is currently used by orthopedicians to understand the gait cycle after surgery. Whereas we use this particular EMED platform in order to understand the pressure points under the foot. So what we do in terms of understanding the pressure point is, here are two case examples. One is a person with high arch and one a person with normal arch. If you look at this, a person with high arch, much of his pressure points are located in this pink region. If and for this person with normal arch, his highest amount of pressure point is located at the front toe. So when he or she becomes diabetic, the first issue would start from here. If you are able to see that the load distribution over here is 545 kilopascals, and on other end, here it's 15 kilopascals. So you can find the difference from top to bottom. So there is a very major difference in terms of the pressure distribution. So at one region, there is a very high pressure distribution, and another region, there is a very low or very limited pressure distribution. So our primary area or the logical idea that we are adopting in this work is, wherever the high pressure distribution is, we need to offload the pressures to the region where there is no pressure at all. And wherever the regions are not in contact with the ground, we want to improve the contact with the ground. It is like the example that we saw, because unless otherwise, if we don't distribute the load over here, as what we have seen in the traditional case, we won't be able to sustain when a person becomes diabetic. This portion is the one which tends to get affected first. So this is where the amputation tend to happen. And we do have our clinical data which proved our theoretical research and the actual practice were getting coincided. So we did happen to observe a couple of people where whom we predicted the high pressure zones, and that was the zone they had the pressure ulcers to start with, and that is from that was the point where the problem started when they become diabetic. So for those people, like what we do is, for now that when we speak of the case study, we collect the diabetic patient. We make them to walk on the pressure platform. We understand where the high pressure zones are. So understanding the high pressure zones, we tend to distribute the pressure, offload the pressure. The high pressure zones have been offloaded to the low pressure zones, and wherever there is no contact, we tend to improve the surface area of contact, and we completely tend to 3D print the foot insole for each and every person based on their foot profile, based on their walking pattern, based on their surface area of contact. It's all been considered, and we tend to print the sole. Here is an example of for a normal foot, wherein a person with barefoot and a person wearing a custom insole. Here you can see earlier with barefoot, there was 70 kilopascals of load was there, and now it got reduced by 30%. And there are some zones where the pressure was low, have been increased, and there were some zones where there was no pressure at all. And now with custom insole, the zones are brought in contact, and the pressure distribution also happens using the custom insole. In earlier case, the pressure distribution was something like this, whereas when a person walks on barefoot, whereas in custom insole, the pressure distribution is within a certain limit range. That means that a distribution is happening within a range of, let's say, 135 to 205 kilopascals is the pressure distribution, whereas in earlier case, the pressure distribution was from 0 to 265, which was a very erratic. And in terms of surface area of contact, we did happen to identify or prove through our work that we were able to reach closely about 15% improvement in terms of surface area of contact. So this is again data which, well, it shows the pressure distribution and the surface area of contact between a barefoot and the customized insole that was developed by us. So this was the EMED sample data. Earlier, we could see a high pressure zone was created, and there were some regions in the foot which was not in contact, but whereas now the high pressure zones have been reduced and much of the foot brought into contact, and the pressure distribution is happening in a better manner as compared to the previous one. So finally, we also split the foot into a couple of zones, and zone 2 were in the mid zone, midfoot. It was reduced by 6.3%, and the zone 3, it was about 27%. On an average, we brought down the pressure distribution by 30%, and surface area of contact was improved by 15%. So not only from this perspective that we analyzed, we also looked in from the traditional Indian medicine perspective, the acupuncture and the Ayurveda perspective as well. And we could understand that the arch region, so through our work, what we did is the areas which were not in contact, or particularly the arch region was not much in contact with the traditional shoes or with the regular custom insoles. Whereas when we came down with our research work, we improved the surface area of contact. That way, we made sure the arch region was also supported. So the arch region was the region wherein the pancreas tend to touch the ground, and when this doesn't get activated, we know very clearly like insulin generation is particularly dependent on the pancreas region. And the insulin generation doesn't happen the way it is supposed to be. And that is where the entire problem starts. Whereas through our research, we did happen to touch these. We tend to give the surface area of contact in all the regions of the foot. So thereby all the nerves under the foot tends to get activated. So this was from the other perspective, and you can Google it for yourself, and you can see the arch region plays a major role in terms of improving the pancreas activity, and we all know that pancreas plays a major role in insulin generation. So this was yet another research work that we came across with, and we did happen to apply for 2 US patent and 2 Indian patent on this. So the key takeaway is we have touched on the lines of static and dynamic loading, improve the surface area of contact, reduce the irregular wear rate of the plantar surface of the foot, and we tend to provide a better customization for the foot. So ideally, our claim is not that diabetes can be reduced. The claim is like we can reduce the time in which a person undergoes amputation, um, or it buys them a time in order to get into the foot problems. So that was the thing that we did through this diabetic foot insole. So these are some of the key takeaways that I would like to deliver. And as we are pretty much close to time, I don't think I would be in a position to touch other um, topics. So I would like to acknowledge Dr. Shrikant, Dr. Vivek, Dr. Adivalagan, and Dr. Shukma, who worked with me on a couple of projects. And I'm pretty much, I'd like to thank you for your patient listening. I'm pretty much looking forward for questions. Any questions, please? Any questions? I'm pretty much happy to answer.
Sir,
Yes, please.
sir, I have a question, sir. So when you use the prosthesis leg,
Yeah.
one can feel the limb pain and back pain, sir. So how we can overcome that, and by using which material we can make it more efficient?
No, like I didn't. Our focus is in terms of using the prosthetic limb. You mean to say the phantom pain? Um, yeah. Our focus was not on the
Yes, sir.
prosthetic side. Our focus is towards treating the clubfoot side. So that is where we focused on, and we didn't concentrate on the pure prosthetics aspect. But I did happen to work on the prosthesis maybe in the somewhere in 2004 in UK, wherein in order to overcome the phantom pain, And because again, the phantom pain starts because of two major reasons. One is during the operation time, if the nerve ending should be enclosed in a right manner. If not, it tends to provide discomfort while the person wears a prosthesis. So we during my research time, we did happen to come across those issues, and we did happen to provide some solutions. The primary solution is the nerve ending should be right, and the second aspect, in order to reduce the pain when they are wearing a prosthetics, is it all goes to the socket. The socket need to be of right size. So the primary solution is the socket need to be completely custom built so that it fits exactly with the transtibial or the transfemoral limb. If not, it would obviously, when they are wearing a um, prosthetic leg, it tend to give a pain. So the socket is the major solution, or the socket is the only solution which need to be highly customized according to the profile of the foot, I mean, profile of the limb, and according to the nerve endings. If they are able to address those two issues, obviously they can overcome the um, issues of wearing the prosthetic limb.
Okay, sir. Good information.
Right.
Thank you, sir.
Thank you.
Sir, good afternoon, sir.
A very good afternoon.
Sir, I have one doubt.
Yes, please.
When doing like this product, it should be lightweight and as well as it has to some withstand some strength. What you have shown in the diabetic foot.
Yeah.
There are many materials like PLA and ABS and PEG material,
Yes.
like nylons.
Yes.
Which material we could choose for this type of applications? Could you clarify that?
Yeah. In terms of it, like I didn't use any of the market available ones like PU or PLA or or any of the traditional footwear based materials. Like I used a material which was obtained from polyjet printing, which we called as full cure, and we used it with show harness level varying from 40D to 60D. That is the show harness level we kept, because as I mentioned during the research work, that there are some regions where we need to offload the pressure and some regions where we need to load the pressure. So wherever we need to offload the pressure, we improve the elasticity levels so that the pressure distribution can be reduced, and wherever we didn't need to be offloaded, we increase the show hardness so that it can take up the load. So for our requirement, what we completely relied is we relied on the raw material that we got for polyjet technology. So that is where we used. But in current situation, if you are using a PU or any other material market available one, either it tend to be too elastic.
Hello, sir.
Sir, we couldn't hear you, sir.
Sir, வெளியே இருக்காரு சார். ஹலோ சார், அது Hello, sir.
Am
Hello.
I audible?
Yes,
Like,
sir.
hi, I had some net issues, so it suddenly got disconnected. Yes, please.
Okay, sir. Sir, few minutes before you said that you have chosen a custom-made material for diabetes food
Yes.
system.
Yeah.
Sir,
Uh,
any that is whether you are trying for commercialization for this product, sir?
yes, we are. I'm trying to commercialize this particular product. I'm just waiting for one of my patent to get cleared. So once it gets cleared, I would be going for commercialization of this product.
Okay, sir. All the best wishes for your efforts, sir, and it was a very informative.
Uh, Thank you. Thank you.
Sir, I have one question.
Yes, please.
Sir, what about the patent you have filed, sir?
Yeah.
Actually, we are also working on some concepts, sir.
Hmm.
I'm filing up to the Form 8.
Okay.
Whether it is request that is needed for Form 18.
No, it depends because you have two major categories. Whether are you doing a product patent or a process patent. If it
Okay.
is a product patent, you don't need to go for that. But if it is a
Okay.
process patent, yes, you need to go for it.
Sir, can you explain more about the product and process? There are I heard about that is utility pattern and design pattern. This is a two
Okay.
category.
Ideally, the design pattern is otherwise called as product pattern.
Oh,
Let us
okay.
say your like this custom footwear,
Mm-hmm.
the individual sole
Okay.
with the different types of materials that I'm putting, and what is
Okay.
the combination of material that I'm using, that falls under the category of product pattern. The design
Okay.
in which I'm doing, that all falls under the category of product pattern. Okay.
Okay.
But
Okay.
for making this design, I need to get the data,
Mm-hmm.
and in order to get the data, I need to undergo, because when you ask a person to walk on a platform, you can't straight away use that data straight away. We
Yes.
need to go for a couple of iterations.
Okay.
We make them to walk on certain trials, and
Okay.
walking on certain trials, within that we have a selection procedure. We
Mm-hmm.
wanted to see how the gate pattern is, how the gate lines are striking, and
Okay.
how the pressure distribution is happening at each stage.
Okay.
Because once, if you try to change the gate pattern, and if we try to customize the insole, the person will not feel comfortable wearing the shoes.
Yes.
Okay. And second thing is, once if we change the gait pattern, then it will start impacting their bones. Initially it starts with their knee bones and the ankle bones. The load will start getting distributed over there, and in future they will have this ankle and bone pains. So we
Okay.
want to make sure that doesn't happen. In order to do that, we have a certain parameters which we test. Those are called as process patent.
Okay. Okay, sir. Fine.
Okay. So it
Yes.
doesn't deal with the product, but it deal
Got it.
with the process involved with the product. So that is where the
Okay.
process patent comes, and that is where the product patent lies.
Okay. So one
Okay.
more, like
Yeah.
drafting of pattern, like I have drafted something.
Hmm.
Uh, Whether we need some attorney to process that, or from ourselves. As of now, like I have processed all those things.
Hmm.
So what is your suggestion? Whether we'll move for go for an attorney, or our side itself we can try.
I worked on roughly about 8 patents, and all
Okay.
those 8 patents I worked with the attorney, because
Oh,
working with
okay.
the specialized patent attorneys will really help you to move your patent forward.
Okay.
Okay.
The attorney, they're charging more amounts, like 60,000, 80,000, because
Yes.
it's not cost that much. No.
Yeah. In my case, since I had specific funding for this, I went through the attorneys.
Okay.
But in your case, if you're spending from your own pocket, I think you need to find a way to get around
Yes.
this.
Okay. Okay, sir.
Yeah.
Yeah.
Okay.
Yeah. Fine, sir. Fine. Thank you, sir.
Okay. Thank you. Any other questions? And I'm pretty much sorry for the interruption that had happened. Some net issues.
No issue.
Thank you. Any other questions, please?
Professors, if any clarifications or doubts, you can ask, sir. Sir is waiting. Otherwise, we can wind up the session. If any clarification, you can ask. Feel free to ask. Sir is waiting. Okay, we can wind up the session.
Okay. Um, okay,
Sir,
then I'd like to thank you everyone for the patient listening, and thank you all, and thanks for the organizer, and thank you for your time.
Thank you for sharing your expertise, sir. It was glad to have you.
Thank you.
Thank you.
Thank you.
sir.
Yes, sir.
Sir, if any doubt regarding this in future, could we contact regarding this, sir?
Yes, sir.
Could you
Yes,
give
sir.
because
Yeah, yeah.
our scholars are very much interested in these applications.
Sure, sir. My sorry, I'm not using my laptop now.
Okay,
As I had some internet issues, I'm using my phone, so that's why I couldn't display my slide.
okay.
You can make a note of my email ID. You can contact me through email.
Yes, sir.
Much better.
Wait, sir. I will open.
Yeah.
Yes, sir. You can tell me, sir. I will take note of that.
It is Dr. Dr. Rajesh Ranganathan
Dr. Rajesh Ranganathan.
at gmail.com.
Okay, sir. Thanks, sir.
Thank you. I
Thank
have as well pasted it in the group. So anything you're pretty much fine to contact
Okay.
me through my email. Yeah.
Okay. Thanks,
Thank you
sir.
then.
Thank
Thank you. Thank you all. Thank you.
Now, I'm delighted to invite Dr. Arun Tom Matthew, who is working as a professor and dean in the School of Mechanical Engineering at Vellore Institute of Technology, Vellore. He has completed Bachelor of Engineering in Mechanical Engineering from Bharatiyar University, Coimbatore, and Mastered in Computer Aided Design from Anna University, and holds a PhD in Assembly Sequence Planning from NIT Warangal. He has filed 5 successful patents and published notable papers and books. He has worked on various consultancy projects and is currently working on design and development of digital twin for rotating machineries fault diagnosis in smart manufacturing under Autodesk Private Limited. He has published 2 books under Springer Singapore Publishers in the year 2019. We welcome you to enlighten us about your view on 3D, 4D printing the future. We welcome you, sir.
Thank you, ma'am. Very good evening, or good afternoon, should I say, to all the members of this faculty development program. I hope you had a good morning session. So, without taking much of your time, I think we will get into the discussion of what we are trying to do today. I hope you can see my screen. Can you see my screen?
Yes.
Okay. Right. We're going to spend the next 30, 40 minutes talking about what is 3D printing and give a hint about what is 4D printing. Very interesting phase that we are into. I'm sure you would have understood that many people are aware what is 3D printing, but still I thought I will take you to that journey once again so that we get a better understanding of what is 4D printing. So we will spend some time understanding 3D printing, the applications of 3D printing, and then slowly we will get into what is 4D printing. Where are we now and what is the future that holds for us? So to begin with, primarily additive manufacturing is referring to a process by which digital 3D design data is used to build up a component in layers by depositing material. So this is the actual definition as per ASTM standard. Digital design data is what we're looking for. Basically, in our language, basically CAD data. Right? So first let us understand what is the 3D printer process. Earlier, we used to work with in 2D, print paper. Be it color or black and white. We used to print in 2D. But with the incoming of 3D printers, we are trying to print a component in the third dimension, the Z-axis. Thereby, you are able to touch, feel the product in a scalable manner, and not just an image. So this gets a customer or a team member to understand what is the product all about. So this helps in a lot of ways because you are able to create this prototype in a faster mode rather than waiting to manufacture the whole product. The additive manufacturing has multiple things. So in that, you get the term of rapid prototyping. Like I just said, people are trying to shrink the time to make the product. So we need a prototype so that we can touch, feel the product for discussion and to get a better influence by the customer. Now, all the 3D printers are 3D. So thereby you are able to get in all the 3 dimensions instead of just pictures in form of paper. So when you talk about rapid prototyping, rapid means the term is definitely very vague. It can take you sometimes 3 hours. Sometimes it can even go to 72 or 4 days to print the whole complete product, depending on the size and the complexity of the particular product. It can be even a component of the product, but depending on the complexity, the material that has been used, the timeline can vary to print the particular product. right? So, like I said, this rapid is debatable. So it all depends upon how you view the product, kind of product, the understanding of the complexities that you want to provide in the product. But when you compare it to a traditional manufacturing process or a subtractive process where we keep removing material from a larger piece of junk, this is quite fast. Hence the term called rapid prototype. So, like I said, there are innumerable uses or advantages of using this. First is, since you can touch and feel the product, it's easy to communicate to the customers, to your stakeholders, to your teammates, what is that the product is all about. Plus, you can scale the product into even, depending on the size of the product, you can go for 1:1 ratio scale, or even go 1:2 or 1:4, or whichever ratio you wish to make the prototype, you can make it and present it to your team. So even this prototype can be used as a tool. You can go ahead with manufacturing the tooling for this particular product, so that it can be used for as a proper manufacturing when you have decided all the dimensions after the prototype. And nowadays, with a lot of technological advancements, you can simply make not just the prototype, you can actually make the finished product directly using the rapid prototyping technology. So you don't have to wait for a crude model from rapid prototyping and then try to do a lot of finishing to make it a production-based component. You actually can get a directly ready-made production-based quality product from your additive manufacturing process. That is the kind of the technology that is coming, is there in the market as well. So the RP technique, or the rapid prototyping technique, as a simple 5-step process, I'm sure most of you are aware of, is fundamentally you have to create a model of your data. So this model you have to convert into what we call as a stereolithographic file. STL format is what we call it. Technically, STL stands for Standard Tessellation Language. Okay, Standard Tessellation Language. So it's a format like any of our CAD designers use. We have X_T, we have Parasolid. Okay, we have IGS formats. Likewise, we have STL format, which is nothing but a Standard Tessellation Language. In commonly, it's called as a stereolithographic file. So you have to convert this file into STL format and then feed this file into the software, so that before we actually do the printing process, we have to slice the file into n number of layers. Because end of the day, since you're adding material, you are adding layer by layer. So how many layers are you going to print to finish the product depends on the kind of machine that you're trying to use. So the size of the layer can be customized, okay, so that the simple as the layer thickness, okay, and then start constructing the model on top of each other. Finally, once the product is completed, you just have to take it out, clear it up, and then the model is ready. So, slightly going deeper, CAD. Nowadays, literally every software, you take Pro-E or Creo, you take Fusion 360, you take CATIA, SolidWorks, any software per se, you are able to create very accurate models in CAD. Okay, and once you are done with the CAD model, if you think that this is good enough, you're happy with the model, all you have to do is start doing the process. So sometimes what happens is some industries prefer to make the CAD model from scratch, or sometimes what happens is there's already a product existing in the market, you want to redo it so that you can make some modifications. You can use a 3D scanner or a profilometer, or what do you call it, a CMM machine, coordinate measuring machine, to get the coordinates of the product, so that you are able to get the 3D model into your system. So once the model is made, what happens is you have to convert the system. The software are such that you are able to convert this CAD model directly into an STL format. So this is the standard format for 3D printing or rapid prototyping or whatever you call it as. So this is the standard format. Even now, the people use .stl file as a format for rapid prototyping. So once this is, like I said, STL format is standard destination language. Destination is nothing but you are meshing the whole component, and in this case, it is basically three-dimensional triangles. Okay, it's all planar triangles, and you don't have the hexagonal element or tetragonal element. It's basically triangular elements. Okay, so you actually mesh the whole component, and in this case, a triangular mesh is used, so it's called as STL format. Right. So in the third step, what we do is before we actually start printing the component using a rapid prototyping machine or an additive manufacturing machine, what we do is we need to do some pre-processing. Like I said, we have to slice the product into n number of layers depending on the kind of machine we have. So some machines may support 0.01 mm. Some machine can even go to higher thicknesses. So depending on the kind of material you're using, depending on the kind of complexity you have in your model, you have to give the layer thickness, and thereby you be able, or if are actually self-driven. That is, once you feed the program into the system, program is nothing but your G code. You can see, you can see that you have a big volume over here, and then to the machine, forget about it because it's upwards in the Z in the direction. So you're able to create the image on a consecutive basis, layer after layer, without any stoppage. So once the product is done, what happens is you have to take the product out because it requires some finishing, because you may have used a lot of powders may be there. So you have to do the final processing of removing the product from the machine, because there's a laser that is involved, the product can get stuck onto the bed. So you have to remove the product from the bed of the machine, cure it, okay, do some minor cleaning. Sometimes, depending on the material, you have to do some kind of surface treatment, and then it is ready for use. Use in the sense, basically, to display the model to the customer. So, depending on what you are trying to do, you can do some painting to the model or some fine touch so that the model doesn't look very crude. Right? So, additive manufacturing, but one of which, the pioneer technology which came into existence, was the stereolithography process, and this was patented in 1986. So here you can see that this technique builds the product from liquid photosensitive polymer, which solidifies when exposed to UV light. So you can see in the previous slides, you have a laser that is hitting the UV, and the moment it falls onto the liquid polymer, the polymer solidifies. So you can actually control where exactly are you able to hit the laser, and you can control the laser, the position of the laser, and the power of the laser, so that you're able to solidify the product at that particular layer. Okay, so typically the 3D printer is nowadays looking like this. We have to input the G code into this, which is nothing but your program, and then we have to print it. So typically, you can see if you slice, you can see a product which is made by 3D printing, something like this. Okay, this is basically a out of paper. Right. So this is not, I will not say it's a new technology. This was already existing a long time back. It is that we were not aware. The idea of 3D printing came in from the Greeks. And if you look at some of the existing structures, let's say 1806, okay, you can see that they actually build layer by layer like this. So that means people are aware of building products like this. Is that the name 3D printing wasn't there, but the idea was still there. So the hero of the 3D printing process, even though the lot of published literature accounts to Kodama in Japan, who built the 3D printer. The actual credit goes to Charles Chuck Hull of the 3D printing, 3D systems, who first developed the prototype 3D printer. So he called it stereolithography, and he developed the STL5 format, which is still used as on date. Right? I hope you are able to understand. Please let me know if you want me to pause or answer any questions. Right? So with this, we'll slightly get into the applications of how this technology has evolved and then where all it is used. Okay. First, it is used primarily in industrial design. Okay, and to a wide extent because designers create a lot of new products, and they don't have time to to reduce the time to the market. They prefer 3D printing or additive manufacturing so that they are able to build the product faster, a real product, and they're able to showcase their product to the customers. Okay. Likewise, this is also used by most of the automotive and aviation industries, so that people are able to appreciate the kind of product that is there in the any product that they are able to make. Likewise, in architecture, any complex model, they are able to see and make so that the community is able to appreciate the design per se. Nowadays, interestingly, even 3D printing has got applications in food. Okay, you can see that people are able to print different shapes, complicated shapes. In fact, even shapes of children to celebrate their birthdays. Okay, so all you have to do is scan the face of the child, and the remaining process is always the same. Once you have the cat model, then it's just a matter of clicking the buttons, and you have to use food-grade material for your printer, and then you're able to print various chocolates, which can be actually consumed. Even in the medical industry, nowadays 3D printing is been getting into extensive application. And you can see that some of the examples I have put is, used by the doctors in dental surgery. Case of accident cases, where you can see the jaw is actually replaced by titanium-based support system. Another example over here is, this is an example I've taken from a partner who works in Mumbai. They have a 3D printing industry. You can see that this is a patient. She underwent a skull fracture, and you can actually see that this much portion of the skull was actually missing. I mean, it got damaged, so they had to operate, and it's open. Okay, interestingly, they were able to graft the skin over it. Okay, but what happens is, because the human body has a pressure inside, the skin alone was not able to have the same profile of the head. So they had to have some kind of a support system inside the skin. Okay, so what they have done is they have actually done a 3D scan based on the X-ray and the CT scan data, because you need a lot of accuracy over here. And they printed what you can see, this piece of skull in titanium. Okay, of course, it's very expensive because titanium is expensive, and it takes a lot of time because it requires accuracy, and you're dealing with the human body. So, but end of the day, they were able to map the skull, and they were able to print this particular shape. And after this shape was transplanted into the onto the head, they were able to do a graft and cover it with skin. And in fact, the patient is actually happily living. Yeah, another patient I thought I will share a small case is a patient who suffered from oral cancer and literally lost the whole job because of the cancer. So what happened was they have approached the doctors and the technologists to to help them replace that particular jaw so that it's not very the person will not have difficulty moving around and even speaking. So same thing, they have done a 3D scan, X-ray, uh, uh, MRI, and all these things, and they were able to map the jaw, and they were able to build a support system, which is made again made of titanium. So you can see a lot of applications are there, even in the medical field, which again I will elaborate as we go forward. So nowadays, a lot of toys are also made of 3D printing because nowadays you get a lot of toys of various sizes. So people are using 3D printing to make unique toys. So since it's 3D printed, you don't have to go for mass production. You can have custom built, for one particular product alone. You want to have a replacement. You simply can, instead of discarding the whole product, you just have to take the existing product, scan it, and then print it. So just custom-based products you can actually do. In fact, you can actually do this in your own homes because nowadays you're able to buy a 3D printer cheaper than the cost of a normal inkjet printer. So that level, the 3D printer has come to existence. So however complex the structure, you're able to perform the process and you're actually printing the whole product at home. So it doesn't matter what sort of complexity it is, how many is there having multiple layers. It doesn't matter because nowadays technology is supporting the kind of build quality, the kind of material we want, the kind of complexity we want. Even the size doesn't matter now. So you can see literally on the latest Airbus 350, more than 1,000 parts are actually printed on 3D. They are actually used on a regular basis. Even animation cartoons are nowadays using 3D printing. Okay, and like I said, custom fit. People are using it to develop prosthetics for people with disabilities. So you cannot have a what do you call prosthetics readily available. It's actually custom made depending on the measurements of the person. Okay, so accordingly, you have to, you can do the requisite study, and then using the technology, you can actually print the part and then apply it onto your patient. So even nowadays, even the software makers are also enabling this. They are also giving you direct access. They say you don't have to require a CAD system at all. You are able to directly communicate to the 3D printer, and thereby you are able to print simple components at home. Then, depending on the demand, let's say highly customizable, they have also created a 3D printer, and in fact, in this case, they are able to print in space also, okay, under zero gravity. So you can see the kind of advancement that is there in this particular field. So having understood the fundamentals of 3D printing, and plus you also listen to some of the lectures in the morning, I will shifting my gear to the next level. So having understood fundamental of 3D printing, we will see how much more can this help us. So comes what we call as the bio 3D printing. Okay, now bio means basically you are going to use it through the human body. Okay, so the whole process is all the same. Just that what we're trying to do is instead of using plastic or metal or food or ceramic or PLA or whatever it is. Now, in this bio 3D printing, what you're going to use, you're going to use material which are compatible to it. Okay, so can you print using blood vessels? Can you print tissues? That is the kind of printing that is available nowadays, and that is called as bio printing. So for printing, you obviously have to require biomaterials because you have to use materials which are compatible to the human body without any adverse reaction to the human body. So what we do is there are 4 levels of materials that have been used over here. The first level is basically to develop medical models or medical devices. Okay, basically non-biocompatible materials. So you know that you have a technology, but you can still use it even though you're not interfacing with the human body. You can actually build a lot of medical devices. Sorry, a lot of medical devices which can be used on a patient. Level 2, you can actually do medical implants. Okay, implants which have been made of titanium alloys or some special grade alloys which are required. For example, you want to put a stent into the patient, a fracture, you want to put a plate inside. This can be actually 3D printed, and this has to be done using biocompatible material. Okay. Likewise, if you go to the third level of bio printing, you have to go for tissues. Basically, you have to be printing scaffolds, which are biocompatible, which are biodegradable, and they are also bioabsorbable. So that means no harm to the human body. So that is the kind of tissue we are going to print. The level 4 biological models, we are actually printing the human cells, okay, using them as materials. So you would have read or heard in various forums or various literature that people have started printing human heart, they have printed human kidneys, a lot of things. So the kind of work that is happening, people are able to adapt 3D printing technology into medical products. So like I just elaborated earlier, we can actually customize implants to different people. You can see how this particular person had because of the skull fracture, you can see the cavity over here, but we were able to replace that particular cavity using a 3D printed material, and you can see that his face is actually saved. Okay, people will not know that there was a major accident over there or a cavity. Likewise, personalization and customization. Like I said, different people are having different properties. Okay, blood groups can be different. The tissue can be reacting different. So you have to be very careful when we are doing this particular modeling because it is patient specific. The modalities for a patient can be different because the patient can be suffering from different ailments. So based on the kind of approaches we have, we need to select the correct material so that it doesn't react with the existing condition of the particular patient. Yeah, so what we do over here for the biomodeling is we definitely do not have a CAD model ready-made. We have to depend on a CT scan or a MRI scan image. Okay, so having got that particular image, what we do is we do a 2D segmentation, then we convert that into 3D image totally. Okay, so depending on the kind of data that is there, we actually can directly go into a medical CAD interface and convert that into an IGS file. Or we can actually look at reverse engineering what we have got, and then from the reverse engineering interface, we can generate point cloud data. And from the point cloud data, we can actually generate the surface, okay, render it. So that end of the day, we get an IGS format. Okay, so depending on the kind of input that you get, okay, all you have to do is we have to convert that whole image, whether it's a CT scan image or an MR image, into a CAD. So you can see that once that is prepared, you are able to print the product, in this case tissue, but in this case what you have to do is your environment should be more controlled because you're going to print a tissue which is can be used in a human body. Yeah, so the kind of application that is there, it has a lot of potential for working in this particular area, because you can see, as I've put up for you on your screen, the global 3D printing market is literally 1.8 million in 2021, and it's going to hit around US dollars 8.3 billion by 2030. So you can see the growth rate in this particular bioprinting market. Okay, because people have understood and appreciated the kind of what do you call it? Kind of support you can get from 3D printing technology into making tissues. In fact, nowadays people are able to even print skin for the human body. So just to give you an idea of what is happening in this area, after the COVID, or I will say because of COVID, the demand for 3D printing, bioprinting has actually increased. Okay, you can see the graph that is there. Okay, the market is actually increasing, and thereby people are willing to take the risk of bioprinting their own human bodies or whatever, the parts that are required. Another thing you can see over here is the global 3D bioprinting market share. Now, this is a slightly old slide, but still it's still relevant. You can see that people are extensively using in the food and animal product. Okay? People are using also in the medical field, even the dental field. So the like I just said, a lot of segments are covered for bioprinting. It can be component, it can be technology, it can be application, it can be the end user. Whatever segment it is, there is a lot of scope for 3D bioprinting technology. Now, commercially, if you look at what does this require, basically it requires just three things. You require hardware, nothing but a printer. You require a software to process the images from CT scan or from MRI scan or from X-ray, and then you require what we call as a biocompatible material. It can be something called as bio ink or a bio paper, which is actually used to print this material. So if you, let's say, you want to print the heart, human heart, you can actually print it because nowadays you are able to have materials which are biocompatible. Right. So now that we have understood what is bioprinting, obviously there is a challenge, because the moment you say we are going to interact with the human body, the first challenge is that itself. Okay, how do you engineer a tissue which can emulate the pattern of a typical biological structure or a human body? Okay, how do you visualize the complex patterns in 3D of our human body? Thirdly, how do you understand the physical, chemical, and biological basis of such biological patterns? More importantly, how do you fabricate them? So these are the various challenges that are there in bioprinting, but still people are investing a lot of time and money in order to make it possible. And if you look at the literature, some of which I have taken for your own understanding, is how people have actually taken biomaterials clubbed with human cells, okay, growing those particular molecules and then actually printing various tissues and organs. Some examples again here, how people have built GI tract, they have built the tongue, they have built the liver. Okay, all of this they're able to build, and they're able to actually transplant the 3D printed organs into the normal human body. So currently, I would say that all of this is experimental, still in the research phase, but there's a lot of scope that it can be a reality, because still a lot of research is happening, a lot of technologies are evolving. So eventually, a day is not very far off where we can actually 3D print what do you call what is required if a part is malfunctioning, you want to replace, let's say, kidney, you can actually vibrant the kidney for yourself and then replace it. Right. So now that you've understood what is 3D printing and what is bioprinting or 3D bioprinting, what we are going to see is how all of this have been are used to the next level, what we call as a 4D printing. Okay. Now, in this case, when we say 4D printing, is we are looking at technology which can, we are looking at materials that have been used in human bodies, materials that can be used as food grade materials can be used as nylon or aluminum or steel or titanium. All of these materials can be used. But if these materials can be smart enough, that means smart in sense they are able to change their shape with respect to time, then the whole technology changes. And that is nothing but the evolution of what we call as 4D printing technology. So it's a very fast evolving technology. Actually, a lot of papers are getting published in this particular area. So I would recommend some of you to explore this particular area of 4D printing, and then it's actually very interesting because all you require is a smart material, and then you'll be able to do the printing, provided your printer supports the kind of material you're using. So, like I said, 3D printing is very nascent. It was first coined by Professor Skylar Tibbets in the year 2013 during his speech at MIT. Okay, so what he did was, as he defined, the use of a 3D printer in the creation of objects which can alter their shape when they are removed from a 3D printer. Okay, the objective is that objects can self-assemble when exposed to air, heat, or water. This is caused by chemical reaction due to the materials utilized in manufacturing process. So what exactly it happens is, you're actually, it's something very similar to 3D printing. You're actually printing the product in 3D, in a 3D printer. But if the material reacts to an external stimuli and behaves differently, then what you call is it's behaving like a 4D. Okay, so basically you're able to give a transformable shape to the particular product. So I'll give you some examples as we go ahead. The materials can have different properties, and so because of these properties, if they are behaving like smart materials, they have a lot of applications. So what happens in a typical 3D printing is you simply have a material in terms of filament or a resin. You use a 3D printer and then you prepare what you call the end result is nothing but a static structure. But in 4D printing, instead of a normal material like nylon or PLA or whatever it is, we are replacing that material with what we call as a smart material. Okay, so obviously your 3D printer has to be different. It cannot be the regular 3D printer because it should be able to handle the smart material. Okay, and then once you're able to print the material, this material, once you expose it to some kind of a stimuli, you can maybe, let's say you want to vary the pH value, you want to increase the temperature of the liquid atmosphere. So you change the temperature, you change the viscosity, you change the pH value, or whatever it is, the behavior of the printed product will actually change and become dynamic. So all that changes is the material that has been used. So you can see that once the product is printed, you simply have to throw it in, let's say, hot boiling water, and you can have different kind of shape. Okay, or you can change the humidity of the atmosphere, or you can project light with various intensities, and you can see that the product is behaving differently. We change the temperature again, you put it dry temperature or put them in hot liquid. Again, you can see the effect of the environment which is causing the product to change shape. So what actually happens is, and technically what we call is, we are able to program the material. So again, if you see that this is again in a very, very nascent stage, And this is going to come up big because of the applications it's having. And literally, you can have this market share will be literally 500 million by 2025, which is right around the corner. Okay, and this there will be an exponential rise in this particular technology because it has humongous applications in military, defense, aerospace, especially healthcare industries. So you can see the number of publications that are there. Of course, this is slightly, I will say, an old data. I'd say I will date it to 2019 December or something. You can see the number of publications that are there are actually very less. But of course, like I said, this is slightly old data. If you look at the latest data, there are a lot of people working in this particular area. Even in India, a lot of people are working, and people are able to print smart components using 4D. So this is an example for you to get an understanding of a 3D printed, 4D printed flower, and this was done at Harvard University. I'll just play this particular clip so that you understand. You can just check it towards the end of the presentation. So there are three primary paradigms to 4D printing. The first approach is you have a smart material which can change its shape to form new structures just by applying different kind of stimuli. Change the temperature, change the atmospheric condition, you change the pH value, you apply light source to it. Depending on the kind of stimuli, the smart material will change its shape. The second approach is you are 3D printing a polymeric material which can act like a support structure, okay, to different organic cells and tissues. Okay, but in this technique, it's primarily deployed in bioprinting applications, which we just saw a while ago. Because in this case, what we require is a biodegradable polymer material which can break down once the tissue is formed. Okay, so that means you need to program the system in such a way that once the tissue is formed, the outer layer is formed, the printed material can simply dissolve. Okay, the last approach is self-assembly of small micro-sized smart particles, which upon stimulation changes their pattern. Okay, so there are several plans and strategies that have been designed to provide the correct methodology for the various applications using 4D printing. So it is not just a simple, like we just discussed about 3D printing. It is not simply any 3D printing process. It's a combination of various components or factors. Primarily, you have to have a 3D printing facility which can handle smart materials. Okay, then we have to look at the stimulus. What is the stimulus that can you have to generate in order to excite this particular material so that it can behave? It can behave the way you want it to. Sorry. Okay, and then the material per se also has to have a lot of say, because are you going to use smart polymer, or are you going to use smart alloys? What is that you're going to use? So depending on the stimulus, the material is going to respond accordingly. You have to choose this smart material. Then how are you going to interact with this particular? What is the mechanism that is there? Okay, and at the same time, you also should know the simulation part of it. So mathematical modeling is also required, and all of this forms the basis for your 3D printing technology. So for 4D printing, you need to have some kind of simulation to understand how do you print. You have to take care of the printing management, extremely sorry. Printing management. You have to take care of the software because you need to handle the printer as well as the system, the file, CAD data, and all of these things. You have to have a very good slicer because you need to again slice to n number of layers because we are using the same technology of 3D printing. So you have to print again layer by layer. Okay, we need to have feedback system. So thereby you have to have monitoring software which you get a regular feedback whether the printing is right or not. So depending on the kind of application that I use, different people use different materials. Primarily something called as shape memory alloys. Some people use shape memory polymer depending on the kind of application. And then some people use hydrogels. And there are also some custom-made materials people tend to research and do it so that you're able to print the material. So the first kind of material that has been used is called as shape memory alloy. SMA are metal alloy systems that can exist in multiple unique phases or states when exposed to temperature or load case. So we have a lot of smart polymers, smart alloys available in the market. You have just to know whether what is the response they give to various stimuli. Accordingly, you have to procure those kind of SMAs. Likewise, we also have SMAs which are super elastic. Okay, they behave in a super elastic material, and or you change the phase of the kind of material, the material will behave in a slightly different manner. Okay, or you can actually deform the material, and once it undergoes a deformation, once you remove the stimuli, it gets back to its original shape. So likewise, in SMA, we also have SMP, what we call as spot polymers, which we will see shortly. And some examples I would like to introduce to you of SLA is basically some kind of an actuator over here. You can see this actuator is the world's first industrial grade actuator powered by shape memory alloy. Okay, so the most widely used SMA is called as retinol, which I'm sure some of you may be aware of. It is a combination of nickel and titanium alloy, and it's a smart material. It's basically used in the biomedical field. So like your alloys, we also have some the polymers that are there. So you can actually have ready-made shape memory polymers that are existing in the market, or you can actually mix and match various polymers, understanding the properties, so that you're able to get polymers which behave smart. As in, they are able to give a change of shape and go back to its original shape depending on the kind of stimuli that has been applied to it. So you can see the capability of polyurethane spot polymer. You can see that has the moisture content changes in this particular case. You can see how they are opening and closing. Same thing, an application of self-folding of an origami box. You can see that you have opened a box like this, and once you put that into boiling hot water, what happens? You can see the whole box is wrapping itself. Because why? Because the SMP activates, and you are able to close the box. So you can see over here, when you heat the component will take a shape, and the moment you release the stimuli, it can get back to its original shape. So you can keep moving from different shapes if you have the right kind of stimulus. So as of now, widely used materials for 4D printing are nothing but your polymers and your alloys. Okay, some of the alloys are basically 3D printed, and these are all shape memory based alloys and polymers. Interestingly, it is basically the polymer which is more biocompatible when compared to a alloy, and hence SMPs are more widely used by the scientists and industry at large, so that you are able to print the product with less energy, and at the same time you are able to give a shape to the particular product. So how do you do this? You have a lot of methods to use it. So some people use FDM method to use it. Some people use it as a stereolithographic method, so that you are able to pour the melted base material through the nozzle. So instead of your 3D printer, which acts very similar to 3D printer, you are actually the molten base material of the SMP is used in the nozzle, and then using this particular technology, you are able to print various shapes, and it can act like a smart polymer, which is actually photoprint. Okay, and such kind of components can be, examples like robot arm, okay, or a gripper application, or a dog bone sample can be prepared of the fusion deposit technique. And FDM offers considerable advantages when dealing with the other techniques. Okay, because you can see it's very easy to upgrade this particular technique compared to the others. So in 4D printing, we just see the literature shows that FDM cannot actually produce very highly smooth layers, and that because we want to keep interfering with the parameters, they are unable to produce a highly finished product using FDM. So you can see over here some examples where I have shown is how a shape memory of a 2D element has caused it to change shape. Okay. Likewise, you can also see a self-bending strip, okay, which is able to bend to a shape of a helix, okay, because of its multi-shape memory effect, which is there in this material. Likewise, you can see a gripper application, where you can see that the uh, 4D printed polymer is over here, and the moment you are able to apply some kind of signature or a heat signature to it, what happens is you just lower it, and because of the change of input parameters, it's able to grip the product and then take it out. So even though FDM of 4D printing is widely used, people are trying to imitate this using STL format, STL lithographic machine. Okay, and the most commonly used methods is because of its high accuracy, and it can be used for a wide range of materials. Okay, so some examples I can show over here how they were actually printed initially, and then you can see how they are able to change shape with respect to time, give a response to that particular stimuli. So you can see over here another example. You can see a tissue-based printed material. You can see how a component which is basically straight is able to fold and unfold itself because the kind of material they have been used, which is nothing but a smart polymer. Likewise, you can see another elastomer, thermoplastic elastomer, which is again a smart material. Okay, they are used as self-bending polymers. That means you're able to create a product which can self-bend, okay, which can be used in a prosthetic arm or prosthetic finger or various such applications. You can see how 4D printing was used to create a trachea product in one of our patients. So a lot of advancements are there in 4D printing. Basically, it is so advanced now that you have to have a lot of softwares to deal with the complete range of 4D printing products because we require a, because it's not commercialized. Okay, we have to use non-degradable flat structures. Okay, we have to develop multifunctional smart materials. We have to have high resolution of 4D printing. At the same time, we also have to have fast and effective cost. So all these factors are helping the future of 4D printing in their advanced stages. So a lot of applications of 4D printing. If you look at architecture, you can see that nowadays people are building houses or huge parks, okay, and which can be self-assembled. Likewise, you can see clothing. You can see how they are, the shirt becomes, or clothing can become waterproof, okay, because of the rain. Okay, it has to sense the rain and then accordingly change its shape and give it to the customer. Any questions you have to know? No questions? Right. So 4D printing is again used in a lot of things, even including health things, because there are a lot of applications where you can use nanotechnology in it. There's a possibility of inserting implants into the human body, which can actually self-deform once you have a surgical intervention. For example, let's say a cardiac tube. Okay, it can actually deform once the implant is actually put in place. And this sort of printing requires the liquid to be filled with stem cells, because they can be used to print slices of liver and other organs. Same can be used to print skin. In fact, the shape of the skin can change with respect to the stimuli, because you can see that skin has to is exposed to a different kind of environment, and according to that, they're able to change its color. They can also change the shape. So, just to keep it interesting, what I've done is I'm going to share a paper with you, which we have co-authored, me and some of my colleagues, where we have elaborated the opportunities and challenges of 4D printing of materials for the future. So I would request you, if you get some time, to download this paper and read and have a good reading, so that we have very elaborately given you on what are the different kind of opportunities that are there, what are the challenges in 4D printing, and what are the applications that are there in the 4D printing as of today. So thank you for your patient listening. Any questions I'm willing to take.
Hello,
Yes.
sir. Sir, good evening, sir. Sir, is it
Yes.
audible? Sir, is it audible, sir?
Yes, it is audible. Can you hear me?
Hello, sir. May I ask?
Yes, please.
Sir, you said that in active materials, shape memory alloys and shape polymers. Is it possible to make that shape memory alloy successfully in India, sir? Actually, these are things which are going around in abroad, I think, sir.
No,
Research you are
actually,
not very successful in India.
yeah, we in our lab we actually have made a polymer. We are actually trying to mix different constituents of polymer and making it smart. So we have, before we even print, we are actually checking whether we are printing small samples of the what we call is we are trying to mix different resins. Yeah, sorry, I think I suddenly lost connection. Can you hear me now? Hello, check.
Sir, you can continue, sir.
Yeah. So what we have done in our own lab here at VAT is we have mixed a combination of resins and made a spot polymer, and then we have actually printed the polymer in using our 4D printer, and it's actually we were successful to some extent. It showed some. Basically, what we did was we printed it and we put it into hot water, and it was showing shape memory properties. The challenge in India is we have to do the mixing of the various resins, whereas overseas you can get ready-made smart polymer which can be directly used for the printing purpose.
Okay, sir. Thank you, sir. Another question from my side.
Yeah.
Sir, you said that in 3D bioprinting, the 2D printing of tissues, and how far it's development now, sir? From tissue to somewhat organs like that, using
Yeah, it is
bioprinting.
still a lot of research is happening. In fact, in VAT, we are actually doing it. We have a dedicated facility to do print tissue. They're doing it on a small scale in collaboration with the hospitals around. But it is not yet reached commercialization because, like I said, people have it's all patient specific. So every patient has different characteristics. So it will take time for it to commercialize. But there is a lot of activity happening. Even in India, a lot of activities happening.
Which are another more questions, sir, from my side. I have read your profile that you are working in the digital twin funded by Autodesk India. Could you share the experience that? And I think your PhD in assembly planning,
Yeah.
Monte Carlo analysis.
Yeah, my PhD in assembly planning is basically, what we've done is uh, before the product goes into manufacturing, okay, at the design stage itself, if we can analyze and come up with a sequence of assembly, let's say you have 5 components, if you can analyze how do you assemble these 5 different components, okay, so that you are able to save time, because time is money in terms of assembly. Reduce the time for assembly. Likewise, if you take an automotive component where you're having hundreds and thousands of components, if you can at the design stage itself, if you're able to generate the sequence of assembly, then there's nothing like it, because you save a lot of time to understand what are the different kind of sub-assemblies at the design stage. If the sub-assemblies can be offloaded to a different vendor, all of these questions can be answered at the design stage. So that is what I did during my PhD.
Thank you, Los.
So one more question, sir.
Yeah.
Does 3D printing affect our health if we use it in dental?
Actually, no, because they are 3D printing the component privately. The human is nowhere involved in that. All that happens is they take a scan of, let's say, that you want to have a cavity filled, and it's a very bad, or let's say you want to replace a tooth. Nowadays, what is happening is they are, putting some gum over there, trying to get the shape of it, and then creating that ceramic crown, what they say, in by the dental doctors. But nowadays, what is happening is with 3D printing, they are able to print the crown at a faster rate, and it is ceramic. So all of these are biocompatible. So you are able to print faster and then replace it. Likewise, you are having the implant over there because you have some jaw is also, if you want to repair the jaw, you can actually do a customize that because you're able to scan that particular tissue or the bone graft. You can customize the whole area and then print it, because nowadays all these materials are biocompatible. You are able to do it. So per se, I don't think the patient is affected in any way.
Okay, sir. Thank you.
Any other questions?
Any
Okay,
queries?
so if there are no questions, I think thank you for your listening, patient listening. Over to you.
Thank you, sir. Thank you so much, sir.
Thanks for sharing such great information about 3D, 4D printing, sir. This gave us an interest to know more about this. I hope everyone got a clear understanding about this informative session. Thank you for being here, and we wish you a happy endeavors. Thank you, sir.
Thank you. Have a nice evening.
Thank you,
Thank you,
sir.
sir.
Thank you all the participants who have joined here. This program will be continued tomorrow morning at 9 o'clock. We have the first session. Thank you all.